Good afternoon, everyone. It's my pleasure to be able to introduce our speaker. So today we are joined by Dr. James Platts-Mills, who is an associate professor at the University of Virginia in the Division of Infectious Diseases and International Health in the School of Medicine. Dr. Platts-Mills received his MD from the University of Virginia and then went on to complete his internal medicine residency at UCSF, and then went on to complete his infectious disease fellowship back at UVA. His research focuses on application of quantitative molecular diagnostics to the epidemiology of enteric diseases in children, particularly in developing countries. And his work includes revising estimates of pathogen-specific burdens of diarrhea to understand the impact of early enteric infections on child growth and development. So please all join me in welcoming Dr. Platts-Mills.
All of that was true, I think. Well, thanks so much. It's been a really lovely visit, a long overdue visit to Emory for me. So for all of you who took time to chat with me over the last day and a half on a wide range of topics, from mosquitoes to flu to schistosomiasis. It's been really, really nice, and great to be here for Dr. Garcia Quesada's defense this morning. So I have a pro tip. If Todd is emailing you and saying, I need a title for your talk, and you know you're going to talk about Shigella, but you haven't really decided what yet, write a title that could, like, honestly, encompass anything you decide to talk about. And I think that I can't, really violate that. At least I'll try not to. So for those of you who were at Maria's defense this morning, she's done a pretty fantastic job of setting up and occasionally articulating better than I am capable of, as is her way, some of the things that I will talk about. I'm going to talk about mostly acute diarrheal disease, a little bit of enteric infectious diseases, more broadly than that. I think the critical thing from the perspective of what I'm going to be talking about is to understand is that diarrhea is not a disease, it is a syndrome. It is a manifestation of a lot of different types of infections. And that provides an interesting context for trying to do work in etiology to try to understand the specific causes of diarrhea. And we're going to get into that into some detail. There are acute consequences of enteric infections and loose watery stools, namely dehydration and death. And there's still estimated roughly 500,000 deaths per year, and it's almost all in sub-Saharan Africa and South Asia. There are also longer term consequences of enteric infections. Okay, so when I came back to UVA to do my infectious diseases fellowship, the Gates Foundation had just gotten interested in reducing under 5 mortality, and they recognized gastrointestinal infections as maybe a particularly amenable area for intervention. There was high mortality associated with it, and it really didn't feel like there should be. It felt like there were acute interventions, vaccines, opportunities to reduce that mortality. And because they want to have data to drive their decisions, they started by funding 2 large multi-site studies, real Rolls-Royce studies, to try to get their first, understanding of what was happening in enteric infectious diseases. The first of those studies was very focused on acute diarrhea. That was called GEMS. And that study was headed by a group at the University of Maryland. And the second was called MALED or MALED, which was a study more focused on the long-term consequences. I'm going to refer to both of those studies a little bit more over the course of this talk. So when those studies were funded, the state of diagnostics for identification of causes of diarrhea looked something like this. This is the workup schema from GEMS. So the idea is child presents with diarrhea, you get a stool sample. It's a good sample. It's downstream from the infection. It's not like getting a nasopharyngeal swab from pneumonia where you don't even really know if you're sampling from the right place. You're not doing a transthoracic biopsy to get something that's established infection in the lung. So it seems like the right sample to get, but then you have to find pathogens in it. And well, you're looking for bacteria, you're looking for viruses, you're looking for protozoa, you're looking for parasites. It's not one fits all in terms of the type of diagnostic you might use. So you might develop some different techniques for culturing bacteria. There are a lot of diarrheagenic E. coli, or these subtypes of E. coli that cause diarrhea because they picked up specific virulence factors. But maybe you need to grow up some E. coli from the stool sample first and then test the individual colonies to see if they have these virulence factors. But should you test 3 colonies or 5 colonies, or how do you do it comprehensively? Just like every single one of these steps in terms of the selective media, all of the bacteriology work, there are a lot of decisions to make about how to do it well. Campylobacter, there are like a million different selective media you can use. And one way of thinking about this is stool is just teeming with bacteria, and you're claiming you're going to isolate the particular bacterial pathogen that you're interested out of a stool sample. So that, you're starting from a disadvantage of having to, somehow separate out the pathogen of interest. And inevitably, you lose a lot of sensitivity when you do that. There are immunoassays for some pathogens, and well, they are not all created equal. The rotavirus immunoassay is quite good. The adenovirus immunoassay is notoriously poor, and so on. Some of them are specific for the subset of virus that causes disease, like rotavirus. Adenovirus, the assay used in MALAD actually was non-specific. It detected any adenovirus, and there's only a subset that are the enteric group F adenoviruses that are thought to cause diarrhea. So lots of problems with this workup. And then the real problem is, let's say you have 100 children with diarrhea, you get a stool sample, you do all of this workup, and you find a lot of pathogen A and you don't find a lot of pathogen B. And then you ask yourself, well, is it because A causes a lot of diarrhea and B doesn't? Or is it because we have a really good assay for A? We have a really poor assay for B. So this kind of diagnostic bias in the test characteristics was a big problem. My mentor for my fellowship, the University of Virginia, had an add-on project to MALAD called Next Generation Diagnostics for enteric infections. And they were basically completely focused on lab development and validation of molecular diagnostic platforms. And the one that kind of won out, mostly because it's nicely quantitative and it's a closed system and the labs really liked it, are these array cards that are often used for gene expression. They work just through microfluidics. You have some ports on the back of this card. You extract nucleic acid from a sample and you put it into the port. You then actually put it into a centrifuge and spin the card, and then the nucleic acid moves through microfluidic channels to all of these different subwells. And the subwells have primers and probes for PCR that are developed under universal cycling conditions, and then you just cycle the entire card. So it's a way of doing quantitative PCR for a lot of different things at the same time, but you should really think of it as quantitative PCR. The other thing is that it should reduce contamination and spill, and it's closed. So the kind of post-amplicon concerns about you know, amplified all this nucleic acid and now it could contaminate your gloves and your next extraction batch and et cetera. I think it does kind of on the long term work really well for labs and people in the lab like it because it's a simple closed system. So this is an example of a card we use. You can have enteric pathogens on it. You can have typing assays. You can have AMR targets. There's a whole suite of different assays that have been adapted to this platform. I'll kind of talk about some of them. So we had the really incredible opportunity to apply these TAC cards to the GEMS study. So GEMS had been done. It had been published in the Lancet. Here's what we found are the causes of diarrhea. And the Gates Foundation went to the University of Maryland and said, hey, will you let them retest all of your samples from that study that you've already published? That's like maybe like the landmark study, you know, that you've worked on for a long time. And, you know, everybody wants to please the Gates Foundation. Maybe that's all, maybe in the spirit of collaboration, they said, yes, you know, let's do it. So we retested all these samples. And, you know, this is just a description of the sensitivity and specificity of the received assays, the assay distribution I showed before, and what was detected by PCR. So you can see, for example, I said the rotavirus enzyme immunoassay is a pretty good test. Yeah, so it's about 60% sensitive versus PCR. PCR is going to be more sensitive than any antigen-based test. I mean, we know this from so many examples. That doesn't mean that that additional sensitivity is clinically relevant. You know, I think people are very familiar with this from COVID. You know, PCR can pick up very, very small amounts of pathogen. that may not mean it's the cause. And, you know, the gut is a long tube that is open to the environment. There are pathogens passing through. That doesn't even mean you always have an infection. And then also children carry these pathogens for a long time, and Maria introduced some of these concepts earlier, but, you know, you get more sensitivity and you get more sensitivity across a lot of pathogens, but you still have some work to do to be sure what's causing disease. We'll kind of talk about that. So we articulated two problems when we approached the analysis of GEMS with the quantitative PCR data. The first is that previous diagnostics had variable sensitivity, and we thought quantitative PCR would help fix that, kind of level the diagnostic playing field. The second is that these pathogens are detected frequently in the absence of disease, and actually PCR exacerbates that problem, right? We've amped up detection of enteric pathogens, and you know, we might see in high burden settings that in a diarrheal stool we'll detect 4 pathogens per sample, and in a non-diarrheal stool from the same setting, maybe 3. So it does seem like there's this milieu in the gut at any given time, and then something else shows up. Maybe 2 things show up because the force of infection is so high, but you know, 1 or 2 things maybe show up and then cause disease. So our approach was, let's see if we can use the metric of the attributable fraction and model pathogen quantity as a risk factor. So effectively say, first I have to describe the association between pathogen quantity and being a diarrheal case versus a non-diarrheal control in GEMS. If I see no association, if I say there's X amount of pathogen A in the sample, and I can't tell you if that's a diarrheal stool or not, then we're arguing it doesn't really seem like that's a cause of diarrhea in the settings. There's no like kind of, you know, epidemiologic inference to etiology. And then once you have that, you can combine that strength of association with prevalence, and I'll kind of walk you through that in a second. So this was shown by Dr. Garcia-Quesada earlier. Lance, apologies for the y-axis, guilty as charged. You know, one of the fun things is forcing ggplot to use dual y-axes. The person who created it is so just dead set against it that you have to like go into this like deep realm of backdoors to make it happen. So you know, that's stubbornness for you. It's managing to get out, you know, a secondary y-axis despite his convictions. You know, gotta show him. So yes, the idea here is that the primary y-axis is the strength of association, which is the curve with 95% confidence intervals about it. So, you know, for example, you can see that enteroragged of E. coli, as the quantity of pathogen increases as you go from left to right in terms of the cycle threshold on the x-axis, you know, never really has much of an association with disease. We detect enteroragged of E. coli in like 50% of cases and 50% of controls. It seems like those virulence factors are just now broadly disseminated in E. coli and probably aren't a pathotype anymore. Shigella, you can see like a very strong association. Rotavirus, a very strong association. The bars, which is the secondary y-axis, are showing the number of cases that were detected in that quantity band in the dark bars, and then the controls of the light bars. So you can basically see as you get out here for rotavirus and Shigella, you're really only detecting that quantity of pathogen in cases. And you can see across other pathogens, you know, these kind of variable associations, but reasonably strong. I will point out H. pylori because I think that this is kind of a fun concept, right? We are modeling pathogens as risk factors. So if you have a pathogen that when it infects a child, it actually infers susceptibility to diarrhea, it is not a cause of diarrhea, we will model it and attribute disease to it. And I think that's what's happening with H. pylori. When you get H. pylori when you're an infant, it can cause achlorhydria, effectively like loss of stomach acid. Stomach acid is a key, like kind of first gut protector against enteric infections and neutralizes those pathogens in the gut. So children who are chronically infected with H. pylori are more likely to present as diarrheal cases than not be non-diarrheal controls. If that's true, then we see an association with disease. That's a theory. I don't know. There's no challenge study or any description of H. pylori causing loose stools. Okay, so this is this odds ratio and on the x-axis, and then the translation to the attributable fraction, and you can then basically go case over case and say, okay, In this first case that we enrolled, Shigella was detected. Here's the cycle threshold of 20. Our models applied an odds ratio of 8 to that. And 1 minus 1 over the odds ratio, which is kind of the metric of the attributable fraction, is somewhere out here. And so we attribute 0.88 of that case to Shigella. So it's kind of a weird, at the individual level, it's a bit of a funky metric, but then you effectively add those, if you add those AFEs across all of your cases, then you get a population level metric. So no cutoff, no yes or no pathogens detected. It's all just scaled to how strongly, based on the quantity detected, we can infer that is the etiology. And then you do that a bunch of times. I'm going to talk about a couple other studies. I mentioned GEMS and Mallet, which are on the left here. The key is this Mallet study and then GEMS facility-based study. Maria talked a lot about EFGH, which is really, in a lot of ways, similar to GEMS as a facility-based study. And GPS is hospital-based diarrhea surveillance in a much broader range of settings, but no non-diarrheal controls collected. And I'll talk a little bit about that. Okay, so what did we find in GEMS? I think really, for me, very helpful in articulating like how this worked and how the the metrics we use work, is you didn't just say, oh, well, we use PCR and now everything amped up, and now we say there's a lot more of this and there's a lot more of this and a lot more of this. In fact, if you look at the top bar in children and infants, our estimate for the attributable incidence, here, of rotavirus in infants really didn't change between the enzyme immunoassay and PCR. And that's my contention, is that there was low-level detections of rotavirus that were picked up by PCR but missed by the enzyme immunoassay. Those were probably not very differentially in cases and controls. And so you kind of increased your prevalence, but you decreased your association with disease, and your attribution stays about the same. Whereas I said the adenovirus enzyme immunoassay really doesn't work, and it was very striking, like 5-fold increase in our estimate for adenovirus 4041. Cryptosporidium didn't change, and then Campylobacter and Shigella increased, and really strikingly, Shigella increased in the second year of life, and looks to be really the dominant cause. And actually, there was a third age range, 2 to 5 years, and I think the Shigella was more than half of all attributed pathogen-attributed diarrhea in those eldest children. So Shigella, a very, very striking with PCR that it was causing a lot more disease than we previously attributed, and some other pathogens as well. And we argued that this closed, the etiologic gap, that when you kind of sum up our attribution across pathogens, in the initial study, it was a little less than 50%, and we got up to close to 90%. There are some caveats to that. The way these are summed, in theory, it can sum to more than 100%, but clearly we closed, the original study was published, and it's like, are we missing major pathogens? Have we not articulated what the major causes of diarrheal disease is? And I think that question, at least mostly, went away with the use of quantitative PCR. I'd also just say that it was very striking that site over site, the differential attribution to Shigella by PCR was quite different. This is Bangladesh, AKA the Shigella whisperers. Even with culture, it looked like they were able to isolate a lot of it. They've been studying Shigella for a long time. They have a lab that's been doing this, as long as anyone. Yeah, maybe that's right. Maybe it's something more intrinsic to the disease there. There are theories about differential sensitivity by culture of different types of Shigella. I don't think so. And then there are other sites where you really saw, very low detection of Shigella. And some of these, over the years and working in these sites, some of the stories have kind of come out like, oh yeah, that's actually, they weren't making the transport media in the right way. And this is an example of where you are trying to rigorously execute and protocolize a multi-site study. And when you're using bacteriology, that is just hard to do. And my favorite moment was at a meeting for a follow-on study to GEMS that was in 3 sites in Africa. And 2 of the microbiology leads from 2 of the sites turned to the third one and said, one turned to the other 2, I should say, and said, are we going to use selenite enrichment for salmonella again? And the other 2 said, we didn't use selenite. And I went back, I was like, oh, I got to see this. And I went back and looked at the sensitivity of salmonella culture versus PCR and GEMS. And it was 80% in the site that used selenite enrichment, and 20% in the other 2 sites. I was like, yeah, there you go. So I think that qPCR does get you away, especially this closed system, from some of that intra-lab variation as well. Malad cohort study, again, like very striking how much Shigella we found, closer to a 5-fold increase where it was like 2.5-fold in GEMS. And I think that tells another story, which is if you want to grow Shigella, you want to collect a stool specimen or rectal swab and plate it immediately. Any lag in getting it to the lab, you lose sensitivity. Malad was a community-based, home-based cohort study where you would leave a specimen collection container. If the child had a diarrheal stool, guardian would collect it, you'd come back and pick it up, you'd put it in a ice box, you'd get it back to the lab, and by that time, I think you had just lost a lot. Another thing that was very striking to us is we've always thought of Shigella as the cause of bacillary dysentery, bloody diarrhea rather than acute watery diarrhea, and this is bedded into the WHO guidelines that have existed for a long time that say if there's blood and stool, treat with antibiotics. If it's watery diarrhea, it's probably viral. I think this is something that Liz has talked about in this setting before, so I'm not going to kind of go down this line, but it's definitely something that we still have a conviction that there's actually, I think that there is undertreatment of watery diarrhea with antibiotics. The question is, can you identify the subset of children where the benefit is greater than, not always easy to articulate risk, certainly some drug toxicity, but also a risk of worsening antimicrobial resistance and et cetera. So one day we will crack that nut. I mentioned GPDS. This is a hospital-based study. I'm just going to kind of very briefly show some big broad results from GPDS, both on etiology of hospitalized diarrhea and then talk just a little bit about diarrhea mortality from GPDS. So GPDS is it was born actually initially it was called the Global Rotavirus Surveillance Network, and it was started by CDC and a lot of partners to generate burden data to help encourage the introduction of rotavirus vaccine into national immunization programs. So they had at their peak 100, it was a massive network of many hospitals in many different countries. And they were all enrolling children with acute watery diarrhea and testing samples by rotavirus enzyme immunoassay. And then there was some centralized reference lab typing and other activities and EQA activities. And these data have now, been collected continuously in a lot of these sites for a long time. And there's, a very nice paper by Adam Cohen showing rotavirus vaccine introduction and showing kind of years prior to years after and documenting the impact on rotavirus detection across a really broad range of settings. So it's been very compelling data. It's supported introduction and it's supported maintenance of rotavirus vaccine in a lot of different places. After we first kind of presented what we had done in GEMS with TACMAN array cards, that network approached us and said, rotavirus surveillance network has kind of run its course. It's done what it was really intended to do. What do you think about trying to broaden it to be a pediatric diarrhea surveillance network? Continue the surveillance in the hospitals in the same way, maybe change the case definition. So not acute watery diarrhea, but just any child hospitalized with diarrhea, select samples, set up your diagnostics in the reference labs. And we said, yes, absolutely. That would be amazing to do. So we have been doing it in a really kind of official way across the whole network since 2017. It's still going right now. Other than the fact that CDC and WHO can't talk to each other, but hey, it'll be fine, sure. You can see, across this network, that rotavirus, Shigella, norovirus, and adenovirus 4041 have really pretty, consistently been the top 4 causes of hospitalized diarrhea. You can also get a sense that rotavirus is coming down. These include, I think in 2017-18, it was about a third of the 30 countries in the network had not yet introduced rotavirus vaccine, and a few had just introduced. So it's really in real time, we're kind of seeing the cumulative impact. The single biggest country in terms of diarrhea mortality in the network is Nigeria, and they just introduced in August of 2022. So effectively all of this data is pre-impact of rotavirus vaccine in Nigeria. But you can still see rotavirus coming down quite a lot, and actually if you subset across all years, only to countries that have introduced rotavirus vaccine, it looks like, Shigella is poised to be the leading cause of diarrhea requiring hospitalization. So that does, really kind of change a conversation about the role of antibiotics in, sick children with diarrhea. Certainly here, if a child has Shigella, they are treated with antibiotics. That's for sure. Another thing that's been influential from that study is our understanding of the age distribution of severe Shigella. So this is there's kind of a long story and a short story. The short story is that the vaccine landscape is crowded with both introduced vaccines and a lot of new candidate vaccines. There is a lot of vaccine development. And there are studies in which people have gone to ministries of health and asked them, what is the next best step for your vaccine schedule? And none of them say, we want more vaccines. They all say, can you simplify the schedule? Can you combine the vaccine into, we love Penta, or, they love these big combination vaccines that are cost effective and very effective for administration. None of them are saying, yes, we want more vaccines. There was a thought that maybe Shigella had an advantage in that a lot of the data we had suggested that a large amount of the burden of disease was in older children. So this is from Malad, looking at children, under 2 years of age, only about a quarter is in infants. So it seemed like, okay, so maybe you can make the case that a Shigella vaccine could be introduced a little bit later, and that could be an advantage because it's the early vaccination schedule that's particularly crowded. Unfortunately, if you look at GPDS and you do the same thing, but you're now looking at Malad is diarrhea in the community of any severity. GPDS is children hospitalized with diarrhea. It's more like 50% of Shigella in children under 2 is in infants. And a third in children under 9 months of age. So these data have also been influential in terms of the conversation about if you're developing a Shigella vaccine, when it can be rationally given, and more. And I think that Maria mentioned the WHO preferred product characteristics statement about Shigella that said immunity should be conferred by 12 months, and they're actually going to revise that to 6 months on the basis of some of this. Another thing that's really important in terms of the burden case and articulating the case for vaccine introduction is estimates of diarrhea mortality and etiology specific diarrhea mortality. And I think I think this is a very thought-provoking question, and just wanted to talk about it for a second. So my contention is that pathogens like Shigella may be underestimated as causes of diarrhea mortality, as such mortality estimates have typically been done. So I'm going to explain how those estimates have typically been done, and then suggest an iteration on that and give you some results based on that. So the first point is that it is hard to study diarrheal deaths directly. Traditionally, I think the argument is pretty clear that a lot of diarrhea mortality happens because of poor access to care. If you have acute dehydrating diarrhea and you don't present to a healthcare facility and get rehydrated, then you're at risk of dying. So you can't just go to a facility and enroll children who died of diarrhea and look at the causes and say, okay, now we understand the causes of diarrheal deaths. You can do a study like CHAMPS, which is probably familiar to some of you, as this is really the home institution or of the CHAMPS study. This is a child, explicitly enrolls children after death and does autopsies to understand the causes of death. That is a really, really hard study to do. It's a very ambitious study, and there have been some very interesting things that have come out of it. But they don't have a lot of diarrheal deaths, and you're certainly not going to get really broad, kind of rapid generation of data across a lot of settings with that approach. So what has typically been done instead is to say we need a proxy. By proxy, we need a subset of diarrhea that we can study and say, what are the causes of this diarrhea? And we can reasonably infer that that's the causes of diarrheal deaths. And the argument was made, and it's kind of been adhered to, that hospitalization is the best available proxy. So diarrhea severe enough to require hospitalization, need an IV to get rehydrated, if you don't present to care, is the sort of diarrhea that's severe enough that you could die of it. So if you enroll children from hospitals and describe the etiology distribution, you can then use extrinsic estimates of diarrheal deaths from something like the Global Burden of Disease study, or from UN, or there are kind of other various sources for diarrheal death estimates from like vital registration data. And you can put those two together. Say there were 1,000 deaths in this country, and here's what we think the distribution of causes is, and put the two together and then sum it off across the globe, and that's how you get diarrhea mortality estimates. The issue with that is I think it's becoming less and less appropriate to say that children die of diarrhea because of poor access to care. Diarrheal deaths have come down quite a lot, and probably improved access to care is a large part of that, and better use of oral rehydration and the available point of care strategies for acute dehydrating diarrhea is part of that. So what if a lot of deaths are now occurring despite access to care? And what is the difference in the etiology distribution of diarrhea that, even though you get to the hospital and get rehydrated, is still associated with mortality? So we wanted to do what we called CFR weighted estimates of etiology specific diarrhea mortality. So case fatality rate weighted estimates. So we said, okay, here's what we're going to do. This is a multi-step process that we have put ourselves through, and you are welcome to poke holes in any or all of the steps in this multi-step process. My pleasure. Okay, so we said, okay, first we need to know at the level of individual countries or individual regions, hopefully, what proportion of diarrheal deaths occurred despite access to care, and what proportion occurred without access to care, because we think that those are different. We think the deaths that occurred without access to care, that etiology distribution of hospitalization, which we get from GPDS, is probably pretty reasonable. But for the proportion who die despite access to care, we think that that etiology distribution should be skewed towards the ones that cause deaths despite access to care, and we have a way of doing that. So we use data from CHAMPS. CHAMPS has enrolled children who died of diarrhea, and they have several ways of assessing whether those children ever access care. They ask whether there's a clinical report of them getting IV rehydration. They also ask the mothers, like, did you bring the child for care? The former is probably conservative, the latter maybe less so. So we created these high and low access scenarios for the Afro region, which is where CHAMPS almost exclusively has data on diarrheal deaths. We then assumed in the Euro region, which is part of GPDS, that access to care should be very, very high. So we said 195%. We then use a metric of healthcare access that's developed by IHME, and we scaled for all of the other WHO regions effectively between these two extremes. All very sketchy, but really fun. Okay, so we kind of then had, like, here's an Afro, we think it's maybe this much access to care. I think the low scenario was 45% of deaths occurred despite access to care, and the high scenario was about 70% despite access to care. And that, it feels reasonable. It's obviously hard to know, and you could try to get, census data or individual level country data, but it's very, very hard to get that to the, to the kind of scope of the project that we're trying to do. So then we take those two proportions for the different regions, and at the level of each individual site, we get two estimates. For those that didn't access care, we just use the etiology, the AS from GPS. We multiply that by that proportion of country level diarrheal deaths from IHME. So it says 50%, we take 50% of the deaths and we apply the GPS etiology distribution. For those who did access care, we weight the etiology distribution using the case fatality ratio. So it's a relative case fatality. So you multiply the AF by the case fatality. That should be divided by, sorry. This should be divided by, so then you divide by the sum of the product of the AF times the CFR, such that you kind of reweight that distribution. And all of these things we have 1,000 estimates of: the etiology distribution, the case fatality rate, and the number of deaths. To get case fatality rates, we used facility-based studies in the subset of children who've been hospitalized. And we looked at and Dr. Maria Garcia Casada produced these CFR estimates. There are some limitations to our ability to do this. There were some pathogens where there was like 1 or no deaths in the appropriate range of follow-up that we had. So for some things, we made assumptions. For example, norovirus and sapovirus had no deaths, so we used the rotavirus case fatality rate. It felt like using a similar, like a viral pathogen seemed appropriate. We thought about like using a mean or median CFR among viral pathogens, but the reason we're having to impute something is because there were no deaths in the, in follow-up from that pathogen, so it felt more appropriate to use the low end of the spectrum. Most of the pathogens for which we had to make an assumption about the CFR were relatively uncommon. I think norovirus is probably the biggest exception to that. So we then apply these CFRs, and there is a lot of data on this slide, so I'm just going to call out a couple of things. So if you look at the global estimates on the left-hand side, if you look at the base case, which is where you don't weight by CFRs at all, we estimated 112,000 deaths due to rotavirus in 2021. If you weight by case fatality ratios for the higher access to care proportion, that's about half, the 68,000. So the argument is, yeah, the more you assume children did have access to care, the fewer of the deaths that you expect to be due to rotavirus, because rotavirus has a very low case fatality rate. You can see that Shigella goes up a little bit. You can see that adenovirus 4041 goes up a little bit, norovirus goes down a little bit. In general, the bacterial and protozoal causes get weighted up a little bit more. From gens alone, that feels intuitive to me. Like for viral diarrhea, you need rehydration. For bacterial etiology, yeah, there may be a role for antibiotic treatment. And in particular, I think there's a lot of synergy with underlying malnutrition. Story. Okay. All right, so I'm going to talk a little bit about then, this is all this burden data we've done, using these molecular diagnostics, that's really helped understand and articulate the landscape around the pathogens that are most, that most need focus for public health interventions, the age distribution of those pathogens, the geographic distribution of those pathogens. But we also want to be able to use these molecular approaches for actually doing trials, treatment trials, efficacy trials. So everything I've talked about so far is doing population level attribution, but that doesn't really work when you're doing an efficacy trial where you have to randomize individual children, you have to follow and say, did they or did they not get the outcome of interest? If they're randomized to Shigella vaccine versus placebo, did they get shigellosis? So I can't say, well, yeah, they had diarrhea and the AFE was 0.8. That doesn't really work. I need to make a call. And so you need a cutoff. We know that if we just say a trace of Shigella was detected, we're going to have a lot of misclassification. And this is also something Maria talked about, these different CT cutoffs that she described, and understanding the sensitivity and specificity of calling true Shigella diarrhea using those cutoffs. So I'm going to talk a little bit about how we derive the cutoff, but most importantly to me about how we then try to support that cutoff and what data we have to support that cutoff. The other thing is that these Shigella vaccines are multivalent vaccines, kind of like pneumococcal vaccine or HPV vaccine, where you're targeting the O antigen on the end of a lipopolysaccharide that's on the surface of gram-negative bacteria. It's very immunogenic, it's involved in invasion, it's a good target for vaccine development, but it's type specific. So the current Shigella vaccines are bivalent or quadrivalent vaccines against these LPS. And ideally, a la pneumococcal vaccine efficacy trials, your primary endpoint would be vaccine strains, Shigella due to vaccine strains, to really see, like, does the vaccine work? Well, how you normally do that is you grow up some Shigella and you use antibodies that are type specific and see if you get agglutination, seroagglutination typing. We don't have isolates because we're proposing to use molecular methods to detect Shigella. So can we also infer the type? So these are the sorts of challenges we had in terms of saying, like, can we use PCR? And I would say, in addition to a maybe less romantic, or I don't know what the right word is for it, certainly a different sort of challenge, which is people saying, well, it's a bacteria. Which is for sure, we have heard, it's like, it's a bacteria, so you need to use culture for a vaccine efficacy trial, you can't use PCR. So, well, it's just, I mean, everything has nucleic acid, why can't we use PCR? But just because something is culturable, maybe, but we can't culture very well, doesn't PCR seem like a good choice? So we've faced those arguments as well. All right, so to derive a cutoff, we effectively said what is the quantity at which the episode-specific attributable fraction is greater than 0.5. You know, a little secret for you if you don't already know. Deriving cutoffs is really hard. It's always a trade-off of sensitivity and specificity. It depends a lot. Are you developing a screening test? Are you developing a confirmatory test? You know, how is this being used? For us, we felt like we wanted something that erred on the side of specificity. We didn't want to miscall Shigella as the cause of diarrhea. And our sense was that this cutoff was conservative and stringent and such that, yeah, there was probably some shigellosis that we were excluding, but we'll take a little drop in sensitivity because we're still getting a lot of sensitivity over culture to maintain that we really think when we're calling Shigella by PCR that it really is Shigella. So I'll give you a couple examples of how we looked to see whether we thought this works. First, this is an example from the Mallard cohort. We compared the population attributable fraction or attributable incidence in this case to the incidence at that cutoff. And for Shigella and for a lot of the top pathogens, it matched up really well. So at least it's nice to say that that individual level call, if you then sum it up at the population level, it seems like we're roughly saying the same burden of disease. We also looked at the clinical phenotype and characteristics of this additional culture negative, but meets our cutoff shigellosis. This was work that we did with Patty Pavernak, who's at the University of Washington, in the GEM study, and she described a similar severity, risk of hospitalization, risk of dehydration between the two groups. Risk and dysentery was equally likely. The biggest difference is that culture negative PCR shigellosis was more common in infants. For whatever reason, it seems like we pick up more additional Shigella by PCR in infants than in older kids. It could be that older kids get more dysentery and so less watery diarrhea, and culture works a little bit better on that because it's less diluted. Another thing we did is collect dry blood spots from children. This is in the EFGH study, which is similar to GEMS, a facility-based study. So we got very small pinprick blood samples from children when they presented with diarrhea and 4 weeks later. We then measured the change in IgG to IPA-B, which is a conserved Shigella antigen. And we used a Luminex multiplex bead assay for doing this. We then classified all of the samples as being Shigella culture positive, attributed, which means culture was negative, but we thought by PCR it met our quantitative cutoff, detected, which means we detected Shigella, but we didn't think it didn't meet the cutoff, so we think it's kind of a little bit of Shigella there. We can't say that it's the cause, and then controls where there was no Shigella detected by any method. And this just shows the difference in the IPA-B antibody population distribution between samples in those 4 categories. And you can already see there's like a clear shift from enrollment to 4 weeks. So it's just when you should see a peak IgG response in the culture positive and the PCR attributable, and very, very little difference in those additional detections. So that was really nice to see. You can also model the log fold rise in IPA-B. And it tells the same story. There's the control versus trace detection of Shigella doesn't look very different, really doesn't look like those children have an acute Shigella infection, but the additional PCR attributable shigellosis, just like the culture positive, looks pretty similar. A lot of variance in the culture positive, but in general, the numbers are a lot smaller for this. Maybe that's why. We also said, well, if we say, why don't we define an immune response as the independent kind of diagnostic gold standard of whether the child has Shigella. So we said, okay, if there's at least a 2-fold increase in their IgG, we call that the gold standard, that's Shigella. We then do an ROC curve where the cycle threshold is the quantitative predictor and the response is the fold rise, 2-fold rise in an immunoassay. And we, I think, I can't remember if I used accuracy or Yadin index, And effectively you try to, prioritize a sensitivity around 80%. Liz? I don't even remember now. We played with this in a few different ways. I think we prioritize a sensitivity over 80%, and the cycle threshold cutoff we got was very, very close to what our cutoff had been. It was within like a cycle threshold or two. So it's just like this is like all of the things that we're doing to try to establish that this assay works and can be used for an efficacy trial. All right, I'm going to give one more example, which is this need to do typing. So it turns out, fortunately, that there's a reasonably strong genotype-phenotype relationship for Shigella types for Shigella flexneri, which is where these vaccines are really being applied. That means there are a series of genes that synthesize and modify the O antigen and make it type specific. And you can detect those genes. And it's very nice if you have a Shigella isolate and you do seroagglutination typing, and then you detect these different genes, you can get a very, very strong association between presence of the gene and the serotype that is defined. So the question for us is, well, can we just do it from the stool sample? We don't have an isolate. So can we just test for these O antigen genes in any nucleic acid from the stool metagenome, and from that can we infer what type of Shigella is in the sample? And this is a scheme of the relationship between the presence of these different genes and the type. So the way this works is like if you have OAC detected and you have GTR1 detected, there's this line that goes across those two genes. Dark and light is just two different panels of assays, so that doesn't have any significance. But this line touches OAC and GTR1. If you have those two genes detected, then you're type 1B. If you just have GTR1 and not OAC, then you're type 1A, et cetera, et cetera. The other issue, though, is that it's not infrequently the case that there's a mix of different Shigella in a stool metagenome, and it's not a pure culture. So then we started realizing, well, we can't just say, are the genes present? We need to say, this is, again, like a quantitative problem. So if we say we detect Shigella and the age cycle threshold is 20, which is saying there's a lot of Shigella in the sample, and we detect GTR1 and the cycle threshold is 22, and we detect OAC and the cycle threshold is 34. Well, is that 1B or 1A? We detected both of the genes, so that should be 1B. But the difference between the cycle threshold of 22 and 34 is like 10,000-fold difference in pathogen quantity. That doesn't really sound right. So then we started creating this quantitative algorithm for how much of the genes have to be present. Now you just like kind of stop and imagine now you're going to like, like a licensing body for a vaccine. You're like, here's how we figured out what Shigella is in the sample. First, we use this PCR assay for a bacteria. And we had a quantitative cutoff that we derived using cases and non-diarrheal controls from different settings. And we used this attribution metric, and we said it had to be greater than 0.5. But then we needed to type it, so we did additional PCR for these 8 genes. I still fear, I do think we're being deliberate about it, and we're providing a good evidence base for everything as we go along. But I don't think we're necessarily like in the clear in terms of these assays. What they really ask is that they're fit for purpose. That's the language the licensing bodies like to hear about assays used in efficacy trials. Like, is this the right assay for this? And that maybe we can make the case. So we've done this and created these algorithms, and we're able to describe serotype distributions, give a sense in GPDS of like the degree of homotypic coverage, like how much we think these different vaccines would cover, and I think trying to set ourselves up for being able to use these in efficacy trials. So we'll see. All right, it is 3:51. I was going to talk about like WASH for maybe 5 minutes, but I'm also happy to, stop here and give a little time for questions, given that it's already 3:50. No, I've already covered a lot of ground. It's okay. I mean, I can keep talking for another couple of hours. I think maybe nice to, okay.
I don't know if you're.
Oh, very good.
I just
Yeah,
have
go
a
ahead.
question. I guess when you're working in these high exposure and high burden settings, when there's a lot of co-infection, how are you dealing with either analytically or in writing grant proposals and stuff, advocating for PCR technologies that can't tell you this is a viable infection?
Yeah.
And there might be other DNA, RNA from other pathogens present as well.
Yeah, and it's a really good question, and I would say it is the most frequently asked question when we talk about this work. The first thing I say is like, yeah, I think you have to use the term co-detection. Because what we are for sure doing is detecting nucleic acid from multiple pathogens.
Right.
But at least give us the chance to show you, based on the quantity of pathogen detected, that it's not quite as bad as all that. Like I said, if you look across all the different settings where we have diarrheal samples and non-diarrheal samples, and you just do a correlation between the number of pathogens detected in diarrheal stools on the y-axis and non-diarrheal stools on the x-axis, the intercept, the y-intercept is about 0.7. So there are about 0.7 more pathogens in diarrheal stools versus non-diarrheal stools, and the slope is almost exactly 1, which is to say, in low burden settings, you look in a non-diarrheal stool and you don't detect anything. And you look in the diarrheal stool and you detect about a pathogen. In high burden settings, you have about 3, and then you detect 1 more, so you have 4. So I really have a conviction that most of the time, it's just one thing that's causing disease, and the quantity helps. It's not perfect, but it does help you kind of get down to what's really there. Maria did a really nice secondary analysis of the longitudinal data from the mallet cohort, and she used the attribution metrics, but then she layered on top of that just sequential stool analysis. So when there was a diarrheal stool, ask what showed up, and at least a 10-fold increase in quantity versus the most recent diarrheal stool, and added that as an additional metric. And you can kind of pick up a little bit more that way, and it's a little bit pathogen specific how much more. The other thing I'll say is that like, we have had some questions that have been a little more precise about the relevance of co-infection. So give you a couple examples. The first is, it's very well described that the oral vaccines don't work as well in children in low resource settings and settings that are endemic for a lot of these infections. There's a lot of thought about immunogenicity being the driver of that. But for the rotavirus vaccine, which is kind of efficacy of 90% in Europe and the US, and more like 50-60% in Africa, studies in Africa and Asia, we said, well, maybe the issue is that sometimes a child has diarrhea, they test positive for rotavirus, but it's actually one of the other things in the sample that's causing disease. So we have in 2 licensure trials in India done our diagnostics on severe rotavirus gastroenteritis. So met the Vesicari criteria of severity, was enzyme immunoassay positive. And then we tested for other pathogens and then tried to see like, is that sometimes the cause? And we used this like a test negative design like within an efficacy trial. And it was like kind of one way of trying to get at this. And you do, at least consistently across these studies, you do see a little higher efficacy if you adjust for the presence of other pathogens. But it's maybe like 5-10%. The other thing that we looked at is in those episodes of severe rotavirus gastroenteritis, if Shigella is present, the duration of diarrhea is longer, the risk of hospitalization is higher. So like you can kind of start to see that there's a mixed phenotype. I mean, the hard thing with diarrhea is it's a syndrome. The clinical characteristics don't tell you what's there, but you do see some differences. And that's really compelling to me. It's like everybody would agree that that's rotavirus gastroenteritis, but those other pathogens there do seem to change, like a little bit. And we have a little bit from ABCD, a treatment trial, where if you have a viral pathogen, but you also have a bacteria there, it seems like there's a little benefit of treatment, so it's like some of those are probably bacteria, for example. So I don't know, that we got kind of like different approaches of trying to understand co-infections. There's no kind of perfect model. There was a lot, like we talked a lot about, can we show synergy? Like if 2 pathogens are present, the child's even more likely to have diarrhea, but all of these pathogens individually are sufficient. Yeah. And I think Liz like really convinced me of this. It's like whenever you try to do like interaction models between quantity of different pathogens, it's always like negative. It's always like less likely. The other thing is that you can ask questions like, do see two pathogens together in a diarrheal stool more frequently than you would expect at random. But the epi of these pathogens, the co-seasonality, the exposure pathways that they have in common, the age distribution they have in common, you can't just naively ask that question across like a cohort. You have to like adjust for all of these things that show why they're more likely to be found in the same stool sample together, and then try to see something on top of that.
Have you done any like pathogen community analysis that kind of taking principles from like microbiome maybe, and you look at the set of communities of pathogens that are there, adjusting for these things to look at that your relationship with that?
Yeah, I think, there's more to do, and I'd love to talk about it. And I think, one thing to say is like, that one nice thing is like Malad and GEMS are publicly available data sets, and they're definitely, there's kind of always interest in going back to them. I think you just have to really work through like how you avoid just spurious findings with this stuff. Yeah.
Thank you.
Yeah, I like that. Yeah.
Can you go back to your slide with the data for the IgG blood spot?
Yeah, sure.
And the specificity sensitivity?
Sorry.
Going forward to, I think you have, yeah, that one.
Oh, yeah.
So I was curious if you were able to do a comparison with potentially IgA in the stool samples to see if IgA is a better predictor than IgG, just because it is a mucosal
Yeah.
environment for the pathogen.
Yeah, we haven't, though we submitted a grant to try it. We just didn't get it. So I agree. I think it would be really nice. And maybe like a little bit more sensitive than serum IgG. Something I'm, not gonna get into, but when we collected these dried blood spots, we were very focused on this question of, can we really prove to people that these PCR detections really are shigellosis? But our interest in use of these dried blood spots like keeps expanding. So one thing I got really excited about is the fact that with IgG specifically, if you collect a sample very early on in diarrhea when a child presents, that really should not represent any response to the current infection. It's too early. So you can actually, at the time a child presents with diarrhea, characterize their natural immunity, which means you can use the test negative design effectively to say, if a child has antibodies to IPA-B, are they more likely to be Shigella test negative than to have Shigella, which suggests that antibodies against IPA-B are protected. And we're having, hopefully, launching into a project using these dried blood spots to use it to establish like candidate vaccine antigens for different causes of diarrhea. We've characterized all these episodes exhaustively, using molecular diagnostics, so we could develop like multiplex speed assays for a broad, like across multiple pathogens, potential conserved antigens, and look at this in more detail. So yeah, I think there's a lot. We'd also love to do like functional assays, not just mucosal IgA, but also like bactericidal assays, or kind of do more vaccine development using this resource.
And I guess with this, basically what you were saying, could you also do ratios to IgM to IgG to see relatively recent infection versus historical infection?
Yeah, that's
the cause of agent.
Yeah, that's a nice idea. Yeah, I hadn't thought of doing that. Do you know what would I guess the question is 4 weeks too late to do that? Or do you think 4 weeks is?
4 weeks is too late to do the ratio?
Yeah,
I don't think so.
okay.
You should, it would skew towards IgG at that point, but like if it's a relatively recent infection, you would get more IgG or more IgG. So it depends on what you're looking for.
Yeah, I mean, one thing to say is like the IgG, as these children get older, it's like hard to even show protection because they all have it.
Right.
And so I think you're right that like some other classes may feel like more transient, and it actually helps you.
Yeah.
Because you may see difference more. Yeah, that's nice. Thank you.
All right, we have time for one more question.
Just think about all the slides I didn't get to show you. It's just, you have to invite me back.
What's going on with the Peru?
There's
The Peru one there.
What is going on with Peru? Can you tell me what's going on with? So there's some funky things going on in Peru. One thing is that I don't think I have this slide even in the various backup slides. Don't think so. One thing that's very striking in Peru in the FGH is it has the highest clinical incidence of shigellosis of all of the 7 sites. A. B, the age distribution of the incidence is across the other 6 sites exceptionally consistent, that it increases in the 2nd year of life. Whereas in Peru, the incidence is highest in children 6 to 12 months. At the same time, the seroprevalence of IPA-B antibodies in the 6 to 12 month kids in Peru is the lowest of all the 7 sites. And when we first saw that, we're like, okay, something's wrong with our assay. Peru has the most Shigella and has the lowest antibodies. And then we're like, well, maybe it's the other way around. Maybe these children are naive, don't already have immunity, and that's why they have such a high clinical incidence. And then we start getting to this whole conversation of like, is that actually is there like the force of infection clinical incidence curve? Does it increase, but then it can actually start to taper off? Because, we think about pathogens like, we talk about LTE tech and Campylobacter, where there's so much exposure that children by 6 months of age are already immune. And maybe they had natural immunity when they were first exposed and they don't get sick. And then they never really get disease. And like Peru's actually in a sweet spot in terms of like a slightly lower force of infection. Liz doesn't buy this because Liz is like, well, then why does the incidence go up in the other sites? So it would help to implicate like waning maternal immunity versus,
Yeah, the different prevalence than all the other sites might drive that.
Yeah,
Sensitivity, specificity flip at the bottom there,
yeah, it does seem
just because if there's just not negatives, fine.
right.
And anyway, I was wondering if it had a lot because it sort of carries over the overall one also.
Yeah, it does. Yeah, it
Okay.
does have a lot.
Interesting though.
Yeah. Yeah, no, that's right.
I do have one question from online.
Oh, sure.
Anne, go ahead.
Oh, thanks. Hey, James, that was a great talk. I just want to follow up on the thoughts about sort of co-infection or colonization or that kind of thing. And I know for other clinical syndromes like central nervous system infection and respiratory infection, there's a lot of interest in using host biomarkers and host transcriptomics to help distinguish like infection from non-infection or bacterial infection from viral infection. And I'm wondering, is that even possible with stool? And is that something that folks are working on to help answer those questions?
Yeah, Daniel Lung, who's now at the University of Utah, who did his fellowship with Stephen Calderwood. Do you know Stephen Calderwood? And Ed Ryan, who are at Mass General and both work in Bangladesh.
Yeah.
He got his K was on like host-based, like immunologic diagnostics for causes of diarrhea. And I think he is exceptionally good, exceptionally driven, exceptionally smart, and he kind of gave up on it. He just found it really, really hard to get clear signals. We're doing some, host-based biomarkers, like Liz has a project to see whether you could use point of care detection of like white blood cells or red blood cells in a stool sample, or even components of the innate immune response to Shigella that are in theory somewhat Shigella specific, to try to distinguish Shigella that should be treated at the point of care. I think early days, I'd say like the inflammatory marker stuff is a little less compelling. Maybe like detection of red blood cells is the most promising, and the innate immune marker, TBD. So I don't know. I think it's a really nice idea. I think there's interest. I just haven't, we certainly haven't gotten into it other than, trying to do some like stool based for Shigella specifically. But would love to talk more about it.
Cool, thank you.
All right, I think that's it for today. Thank you very much.
Yes.